try that. Can you see a signal now?
Oh yeah.
Okay, we're good.
Okay. Yeah, you wouldn't get it on the recording. These guys will hear you fine.
Okay, good. Anyway, so 2 reasons. We have access to space, get above the Earth's atmosphere. For the first time, you can see the universe for what it is. Secondly, because of our electronics industry, we've developed sensors that can see all wavelengths of the spectrum, from gamma rays to X-rays to radio and infrared. And so we are literally part of the first generation to see the universe throughout the spectrum. And since 2015, we've opened up a brand new window, namely gravitational waves, which are now opening up new vistas into the physics of black holes and the early evolution of the universe. And finally, an even more exotic window is being opened called neutrinos. What are neutrinos? These are very ghostly particles that emerge from certain nuclear reactions and also very high energy processes. We have detectors at the South Pole. There's a cubic kilometer of ice, crystal clear ice, about a mile underground, that's been instrumented to detect neutrinos. And we've now, for the first time this year, detected neutrinos from our Milky Way and from nearby black holes, which are shining jets in our line of sight. This is just a glimpse of the kind of results we found in astronomy. So that's the remarkable thing. We live in an absolutely spectacular time. This is a brief history. I'm not going to go through this in detail, but pre-1880s, we didn't even have a way of recording images. Everything we knew about the sky was literally gained by looking at the stars with our eyes. With the invention of photography in the 1880s, we were able to, for the first time, to record an image. And then we realized that by exposing a photographic plate for not minutes, but hours, we could see far deeper into space than was possible with our eyes. But still, it was restricted to optical wavelengths, visual wavelengths our eyes could see. By 1930s, with the invention of telecommunications, in fact, AT&T, Bell Laboratories, had a problem. They just implemented in the 1920s the first transatlantic radio telephone service. And immediately they discovered there was excess noise. And so Carl Jansky, an engineer at Crawford Hill in New Jersey, was assigned a task of figuring out what's this excess noise. So he built an antenna, what that was then out in the boonies south of New York, and he discovered that he could see lightning storms anywhere on the planet, 80,000 lightning hits per day. But in addition, behind that static of lightning storms, he saw a steady hiss, which got brighter and dimmer, brighter and dimmer. And this was totally mysterious. It was no one expected radio waves from space. But it turned out that the signal came from the center of the Milky Way galaxy. That research was actually kind of buried. No one followed up except an amateur in Wheaton, Illinois, who built in his backyard a 30-foot wooden telescope, coated it with copper, built his own radio receiver, and for 10 years he was the world's only radio astronomer. He made the first map of the Milky Way in Illinois. With the Second World War, radar was developed, and all of a sudden, the professional astronomers realized there's something interesting here. They started developing radio astronomy. This was our first new window on the cosmos, opened up only in the 1950s, 1960s. And then we realized that there's an entire world to be seen by going to the other wavelengths of the spectrum. But we could not access them because we didn't have access to space until the 1960s. With the launch of the first satellites, we realized there's gamma rays, there's X-rays, there's infrared, and radio waves we can't see from the ground because our atmosphere is opaque to certain frequencies. But to truly take advantage of space, we need to build bigger telescopes. And the first really large telescope was the Hubble Space Telescope, at visual wavelengths. It gave us the sharpest images because it took us above the Earth's atmosphere. We didn't have to look through the turbulence of the Earth's atmosphere. Okay? What has all this led to? Well, first of all, it's a big surprise. Up until the 1920s, most astronomers thought the universe was static, maybe infinitely old, and that the Milky Way was the universe. And then beyond that was this vast emptiness. And then it was discovered by Vesto Slipher in 1913 that these funny nebulae we call spiral nebulae, today we call them galaxies. At the time, many thought that these were protoplanetary systems, clouds of gas swirling around forming stars which were making planets. Turns out that was completely wrong in the 1920s. These things are systems of stars just like the Milky Way. And what Westo Slipher discovered is that except for the nearest ones, the ones that looked small and were apparently further away were moving away from each other. And that was like, what? What's going on here? Edwin Hubble in the 1920s confirmed that measurement. And in fact, what he didn't know is that Albert Einstein had just worked out the theory of gravity called general relativity. And he had a problem. He couldn't make a static universe. His equations told him that the only possible universe is either expanding or contracting. Why? Because it's just like trying to balance a pencil on the sharp tip of the pencil. You can't do it. If there's attraction of mass, either the universe is collapsing or if it has enough energy, it's expanding. So he actually invented a fictitious term he inserted into his equations to stabilize the universe. Called it the cosmological constant. After about a decade, he learned about Edwin Hubble's realization that the universe is actually expanding. He said, oh my God, this cosmological constant was my biggest mistake. Roll forward almost 100 years to 1998. And we were in for another root surprise. The surprise of the 1920s was that the galaxies were receding from each other, expanding away. That was, in fact, kind of a radical thinking, because no one thought about that before until that was possible. There was a prediction, though. George Gamow, back in the 1940s, realized that if the universe is expanding today, that means if you take pictures and run the movie backwards, in the past it would have been denser and hotter. And there was a consequence of that. If it was hot enough, it would have emitted light. Light, like the sun emits light, because it's a hot body. Except because of the cosmic expansion, that light would have been stretched by the cosmic expansion by 1,000-fold amount. So light that was emitted, just maybe twice the wavelength that your eyes will see, today would be seen at a wavelength of order of a millimeter in the radio part of the spectrum. That prediction in 1948 was forgotten until 1964, when another group at Bell Labs, Arno Penzias and Bob Wilson, found, because of the first telecommunications experiment called the ECHO satellite, the steady hiss from the sky, uniform, with a temperature of 3 degrees above absolute zero. That confirmed this prediction that the universe is expanding had a hot beginning. So that was the second kind of real discovery of the mid-60s. But the really interesting thing happened in 1998. The Hubble Space Telescope was built in part to measure precisely the expansion rate of the cosmos. By 1998 what we expected is that because of all the mass of the universe, gravity would slow down the expansion. So everyone sought to measure the rate at which the cosmic expansion was slowing down because of all the mass in the cosmos. By 1998, it became apparent there was a problem. The universe's expansion is not slowing down. It's accelerating. It's as if something, a repulsive gravity, was pushing the galaxies further apart. We give these two terms, this phenomena, we give it the term dark energy. Dark energy. Oh, we must have popped out of presentation mode here. Can you push that button? I don't have it access on the screen here. There we go. Okay. Also, I should mention that back in the 1930s, it was also realized that the motions of galaxies, in groups of galaxies, seem to be anomalously large. In fact, that gave rise to this idea that most of the matter in the universe is invisible, not visible to light or any wavelength in the spectrum. We just can't see it. It's there. We can see its gravity. We call that dark matter because it's not visible to light. The fact that the universe's expansion is accelerating, we call it dark energy. You don't quite know what it is. In fact, I would say that these are two of the biggest mysteries we have in astronomy today. Okay? Fast forward, one of the remarkable things of the last 20, 30 years is that we've started to discover planets outside of our solar system. We now know about 5,000 around stars. And in fact, the rate of discovery is such that we now think that essentially every star has at least one planet. Many have multiple planets. And one of the challenges of the next century, I would say, is to figure out how we can probe the physics of these planets. What are their properties? And big question, is there life outside the Earth? We don't know. We are thinking hard about the tools that are needed in the future to actually answer that question. Are we alone? And if there's life, what kind of life is it? One expectation is most of it might be bacterial. That advanced life forms may be relatively rare. We don't know, but that's one of the challenges of the future. The rest of this talk is going to be less words, more pictures. This is a talk that I developed based upon the launch of the Hubble Space Telescope, not the Hubble, the James Webb Space Telescope, which is currently, I think, the most ambitious instrument we've launched to space. The total cost to develop this mission is $10 billion. It took 20 years. It was launched Christmas Day 2021. And, well, this is just hang on. I got a little ahead of myself. This is our current view of the cosmos in a cartoon fashion. We think we know that the universe is about 13.7 or 13.8 billion years old. It emerged from an ultra-dense state, which in my mind looks very similar to what the interior of a black hole might look like. In fact, I think there's a fundamental connection between the physics of black holes and the Big Bang. We underwent a period of what we call inflation, when essentially, just like dark energy, the ultra-dense birth of the universe exploded essentially. And then ordinary matter condensed, dark matter condensed. 340,000 years later, the cosmic microwave background was released. The plasma of the early universe is opaque to its own radiation. When the first hydrogen atoms formed about 380,000 years after the Big Bang, the light of that hot plasma could start streaming freely through the universe. At the time, if you could sit there at a young universe, 380,000 years old, what you would see is a uniform glow, uniform to a part in 100,000, that was about 1/16 as bright as the surface of the sun in every direction, had a brightness temperature 1/2 that of the sun. Those photons, the particles of light which were emitted, have been stretched by the cosmic expansion by a factor of 1,000, from 1 micron wavelength to 1,000 microns, which on your ruler is 1 millimeter. That's where the cosmic microwave background was detected in 1964. WMAP was a satellite that's taken a detailed picture of that cosmic microwave background. There's other satellites that have done it. And so we have a baby picture of the universe, what it looked like. There were no stars, no galaxies. It was a uniform plasma smoothed apart in 100,000. From that, a few hundred million years later, the first galaxies condensed. And the James Webb Space Telescope was designed to see the first light of those galaxies. This is James Webb. It's the biggest civilian space mission to date. A 6.5 meter mirror, cooled to 40 degrees above absolute zero. It's in an orbit which is 3 times further than the moon. It's what's called an L2 orbit. And what that means, from the vantage point of James Webb, the sun, the earth, and the moon are all within the same direction in the sky. And in fact, that point, that L2 orbit is such that you orbit the earth once a year, just as the earth orbits the sun once a year. So that from the spacecraft point of view, the sun, the earth, and the moon are all in a 30-degree portion of the sky. And that way you can build a giant parasol, a sunshade, that shields you from the light of the sun, the infrared light emitted by the earth, and the infrared light emitted by the moon. And that allows the telescope to just radiate its energy to space, cooling passively, without any refrigerators, to 40 degrees above absolute zero. And the first question is, why? See, James Webb was designed to work at wavelengths of a little bit longer than visual light to 28 times that wavelength, 28 microns. Visual light is 1/2 micron. By going out to these long wavelengths, turns out warm bodies at room temperature radiate profusely at 10 microns. We're all aglow in this room at 10 microns. The telescope has to be cooled so it's not blinded by its own radiation. And so by letting it radiate its heat to space, by shielding the earth light, the moonlight, and the sunlight, the telescope reaches 28 or 40 degrees above absolute zero. By the way, why did we go to the infrared? Well, because of the cosmic expansion. You want to see the earliest galaxies, the oldest galaxies? Well, you have to go to the infrared because the wavelengths of the stars have been stretched by the cosmic expansion from visual light to the infrared. Okay? By the way, telescopes are time machines because of the finite speed of light. When you see the sun, you don't see it the way it is now. You see it the way it was 8 minutes ago. When you look at the nearest star, Alpha Centauri, you don't see it the way it is now. You saw it the way it was 4 years ago. That's the closest star, 4 light years away. When you look at the Orion Nebula, which we'll look at the picture of in a few minutes, you see it the way it was about 1,300 years ago. Okay? The light's been traveling all that time. When you look at the distant galaxies, the closest one you can see with your eye is the Andromeda Galaxy. It's about 2 million light years away, which means that light has been traveling towards us for 2 million years. You are looking back in time. The further you look into space, the further back in time you see. When we look at the geology of the Earth, you go to the Grand Canyon, look at the layers of rock. You have to infer the ages of those rocks. In astronomy, we can literally watch cosmic evolution from the time the cosmic microwave background was emitted to the present. We just have to look ever deeper into space, because the further you look into space, the further you look back in time. We can literally watch galaxies emerge from that cosmic plasma, condense for the first time, make their first stars, and watch them grow to Milky Way-sized galaxies just by looking at various distances. We see back to various times. We can literally watch cosmic evolution. That's one of the remarkable things about telescopes. Telescopes are time machines, okay? So why did we go to the infrared? Well, first of all, the universe is expanding, shifting the emitted light to long wavelengths. Secondly, the Milky Way is opaque because it has dust that absorbs even the infrared light. By going to longer infrared wavelengths, that dust becomes translucent. We can look into places where young stars are being born, places where we simply cannot see what's going on at visual wavelengths. And thirdly, our atmosphere is opaque at most infrared wavelengths. Water vapor, carbon dioxide, methane, all make the atmosphere opaque. And furthermore, the atmosphere is aglow in the infrared. It's warm, it's at room temperature. Well, not today. Today it's about 20 degrees below room temperature. If you had infrared eyes, it would be blindingly bright outside, just like daylight. Okay, so we have to get above the atmosphere to get around that. All right. Most of what I do is star formation. How do stars and planets form? So I'm going to concentrate, using James Webb images mostly, on what we see in places where young stars and planetary systems are being born. And we're going to take you on a visual tour of what we see in the sky. So this is a ground-based image of a dark cloud. You can see stars in the background, a dark cloud here. And you see this funny filament. Turns out to be a jet of plasma shooting out from a forming star you can't see. Where's this star? We're going to go to the infrared. This is a ground-based image taken in the same scene. If I go back and forth, you notice the stars are there. And you see many more stars where the cloud is opaque at visual wavelengths. The cloud is opaque at visual wavelengths. It's translucent in the infrared. And that blazing bright object is a forming star. Now, next picture is what James Webb sees. So here we go. That's the James Webb image. Much sharper. Whoop, keep going backwards. There it is. And if you look carefully, you notice something. Look at these knots. This knot, and this knot, and this bubble. The picture I just showed you here was taken around 2005 time frame. And this was taken just last year. Notice the movement? Tells you that beam of plasma is moving at about 300 kilometers per second away from that forming star. That's what we call an outflow. One of the first signs of the birth of a young star is this outburst of material that flows out along the spin axis of that star. And I'll show you some other examples. Here, by the way, if you've gone back to this part right here with the Hubble Space Telescope, here's what you see. Here's the edge of the cloud, the young star's hidden, a beam of plasma, and 3 years later, this is taken in the 1990s, you can see the movement. Okay, here's another one. And you can see over 2 years, several years, from 2000 to 2022, you can see the movement of knots away from an object which is not visible in the middle. It's completely embedded. Even in the infrared image, the forming star is hidden by circumstellar dust. Okay. This is just a wider field view. There's another forming star right here with an edge-on disk shadow. The spin of dust and clouds because of gravity. As a cloud collapses, even a tiny bit of spin gets accelerated. As an object collapses, the spin gets amplified. The smaller the object gets, the faster it spins, just like what a skater does. You know, a skater holds its arms, spins around. I pull my arm in, I start going really fast. Okay? Circumstellar material collapses into a flattened disk like the rings of Saturn. That's a disk. And in fact, that disk, in this case, is almost edge-on, and in that case, it's almost edge-on, casting a shadow on the interstellar medium in that region. Here's another jet. They're just beautiful objects. Here's another one. The young star is hidden again by a disk right here. There's a flow going this way. There's a flow going up that way. What you're looking at is not what scientists call shock waves. Motions much, much faster than sound speed in the medium. When you slam plasma or even cold gas with speeds of hundreds of kilometers per second into other parcels of cold gas, you heat up the gas to temperatures of tens of thousands of degrees. You break apart the molecules. You even rip electrons out of the atoms. And as those electrons recombine, they emit light. That's what you're seeing. You're seeing shock waves breaking apart molecules and atoms, ionizing them. And as the electrons get recaptured, they emit light. Light at not just visual wavelengths, but at infrared wavelengths that James Webb can see. Okay? This is an object. Actually, we have a James Webb proposal. We're going to get an image of this. This is a Hubble image of a jet. This shows you, there's another view. There's a cluster of stars. These red circles show you the locations of stars. One thing we've learned about star formation, stars almost never form in isolation. Show me a forming star and I will show you hundreds in its immediate vicinity. Most stars form in clusters of hundreds of stars. And we think our own solar system formed 4.5 billion years ago in a cluster similar to the Orion Nebula, which contains a couple thousand stars. We had sibling stars so close to us that when some of those sibling stars, if they were massive, while the Earth was forming, while the solar system was assembling itself, the massive stars in our birth cluster were exploding as supernovae, pelting the forming solar system with radioactive elements. Those radioactive elements are today still responsible for heating the core of the Earth, for generating volcanism, for in fact making plate tectonics possible, which we think is essential for the existence of life on this planet. Venus, apparently, doesn't have the kind of plate tectonics Earth does. And because of that, we think it had a runaway greenhouse. Basically, it lost its water, lost its hydrogen. The atmosphere became so CO2 rich that temperature was reaching something like 700 degrees. Not suitable for life. Plate tectonics is essential for life, we think. Okay. This is just another jet. We have a James Webb observation happening in March of this object. I can't wait to see it. It's going to be fun. All right. So what is the visual sky? How does it compare to the infrared sky? Well, this is, you guys use telescopes and wide field cameras. This is the summer Milky Way, the galactic plane. If you know your Messier objects, you know the Messier 8 object here, Messier 16, Messier 17, and a dark cloud called Rho Ophiuchus. I'm going to first zoom into that region, but what does this scene look like at infrared wavelengths? This is an old image taken with the IRAS satellite in the late 1980s, registered. Notice something. The visual sky is full of stars and dark clouds. When you go to the infrared, 200 times the wavelength of visual light, the stars disappear. The interstellar dust clouds, however, light up. They start to glow. What they do is they absorb the starlight. The dust grains on those dust clouds warm up to a temperature of 20 degrees above absolute zero. And they radiate at wavelengths a couple hundred times visual light. That's the same scene. I'm going to zoom into this region called Rho-Fucus. There it is in the optical. Dust streamers here. Here's the Milky Way. There's Messier 8. There's Messier 17. Messier 16. I should use my pointer. Zoom into that little spot. We took an image here. There we go. This is an image we took, again, I think in 2009 in Chile, in the infrared. See a dark cloud, see a bright star, you see this reddish emission. These are molecules of hydrogen glowing because of shock waves. This scene was imaged by James Webb last year. There's the James Webb view. And notice the difference. Oops. If you look carefully, you'll notice again these bubbles are moving away from the central region right about here. There's a protostar there. There's another protostar there producing this bubble and a bubble up at the top here. Okay? There's a more evolved star here that's lighting up this cavity. But that's what the ground-based image looks like. That's what the James Webb image looks like. All right. I went to M16. I showed you M16, Messier 16, one of the most beautiful objects in the sky, in the summer sky. This is a deep amateur picture of it. You see these gorgeous pillars here and here. If you go to the infrared, that's what they look like. The stars have disappeared. You see the dust emit and glow. Then we go to James Webb. I'm going to zoom in on this with the James Webb near-infrared camera. Here's the pillars that become translucent. We're then going to zoom in. I'm going to go to even longer wavelengths with James Webb. Wavelengths between 10 and 20 microns. That's what they look like. And then just a long wavelength there. The stars are disappearing. Here you can see the stars because we're adding in the short wavelength infrared. And here just a short wavelength by itself. These have been dubbed the pillars of creation because Hubble first took images of this region. The claim was there are hundreds of forming stars in here. Turns out there's about half a dozen. What you're seeing here is a debris of star formation. This is what's left over when the parent cluster, which is just to the north, to go back to this image, right here. That's where all the action happened about 3 million years ago. A cluster of about 1,000 stars, half a dozen of which are massive. They've cleared out their environment, they've destroyed their parent clouds. And what you're seeing here is the leftovers of that star formation episode. Okay. How many of you have seen the constellation of Orion? All right. If it was clear, it'd be right there, just passing transit right now. Orion is the nearest active site of ongoing star formation where low and high mass stars are forming. And this is a deep amateur picture showing you Betelgeuse, red supergiant star, Rigel, another blue supergiant star, the three famous belt stars. And you see the Orion Nebula right here. And it's surrounded by this arc called Barnard's Loop after E.E. Barnard, who found this in the 1905 timeframe on the first deep photographic images of this patch of sky. This is now an infrared, far infrared view taken with the Herschel Space Observatory, actually the Planck Observatory, European satellite. I just want to show you the visual and then the Planck view. And you see, instead of stars, right where the Orion Nebula is, and right where the Horsehead Nebula is, right there, that's the Horsehead Nebula. That little nubbin shows up in emission. This green stuff is dust. By the way, if you know your frequency, this is 545 gigahertz. Really high, much higher than your PC, much higher frequency. This is what Orion looks like. What you're seeing here is a dust associated with two giant clouds of molecules, each about 50,000 times the mass of the sun. So this is the previous picture we saw, visual. This is the infrared of this inner part, just before the Orion Nebula. You're seeing the dust. Here's the Orion Nebula itself. And then if you zoom into that little box with the Atacama Large Millimeter Array in Chile, you see what looks like a 4th of July fireworks display. What the hell is going on? Well, by the way, this is a near-infrared view of Orion Nebula. If you looked at this through a telescope, this should look somewhat familiar. Well, you see many, many more stars because the dust is translucent and we can see deeper into the population of young stars in this region. If you look right in this region, right here, just above the trapezium, you see this. This is a 4 trapezium stars. These stars should be familiar, those of you who have looked through a telescope. Those 4 stars are easily seen through telescopes here. They're the brightest stars in the Orion Nebula. They're responsible for lighting up the nebula. They're massive stars, up to 40 times the mass of the Sun. 90 arc seconds away, something like 3 times the size of the planet Jupiter in the telescope eyepiece. You see what looks like this explosion. And I want to show you what that looks like. This is actually an adaptive optics image. This was taken from the ground with an 8-meter telescope using laser guide stars to actually remove the atmospheric turbulence. We can do this, but it's really difficult. And what you're seeing is it looks like an explosion. Well, if you don't think that's an explosion, let's compare an image taken in 2013 with adaptive optics with a James Webb image taken last year. Now, these are not perfectly registered, but you notice that the upper part, things are moving. So let me show the full field. This is comparing an earlier 1999 ground-based image with a James Webb image. See the movements? If you didn't think that was an explosion, you can see the movements. I'm going to zoom into this a little bit. On the lower right hand of that image, you can see these shock waves moving out. And this is about a 22-year interval. So you ask, when did these things originate from a compact core? And what happened there? Well, the answer is about 550 years ago. That's when the signal would have gotten to us. Now, remember, Orion is about 1,300 light years distant. So the actual time of this event was about 1,300 plus 550 years. It's about AD 170, the height of the Roman Empire. What happened in Orion? And how much energy is involved in that explosion? Well, we went, by the way, something to point out here, there's a star. See that little blue circle right there? That star is flying out from the same region as the gas. That star is moving at 55 kilometers per second away from the explosion center. What happened here? What other clues do we have? Well, if you go to millimeter wavelengths, Atacama Large Millimeter Array, you see carbon monoxide. Carbon monoxide is a common gas that traces molecular gas in these interstellar clouds. And from the carbon monoxide, we learned there's something like 20 times the mass of the Sun involved in this explosion. The fastest ejecta is moving at hundreds of kilometers per second. The total energy, it's more energy than the Sun puts out in 10 million years. All that energy was produced 550 years ago in some cataclysmic event. What happened? Well, our best guess is that several stars in a dense forming cluster interacted. 2 of them merged, coalesced. And the gravitational potential energy is what released the energy that's driving this explosion in the gas. That's what we think happened in Orion. Cataclysmic explosion driven in a very dense forming cluster. Why do these stars interact? Because inside the molecular cloud, the environment is viscous. As the stars orbit each other in a mutual gravitational attraction, the gas acts like a medium which removes the orbital energy of motion. The stars get closer and closer and closer together until they merge. The physics is a little bit more complicated because you actually think that the interaction really involved 4 stars, 2 of which were in binary. So it was a binary-binary interaction. 2 stars merged to produce one of the stars in the middle. By the way, the stars that merged, we think, is this object here. It's 15 times the mass of the Sun, flying out at about 10 kilometers per second. There's this star that we just saw in the images, 3 solar mass star flying out at 55 kilometers per second. In the opposite direction, there's a 10 solar mass star flying out. Evidence that there was a violent interaction in the star-forming region. All right, that's Orion. So that's a little bit about how stars form. Star formation is a violent process. It involves, most stars form in clusters. The massive stars are exploding as supernovae at the same time, while the low mass stars are still forming their planetary systems. So what happens? Stars live by nuclear fusion. The sun will live about 10 billion years. But the massive stars, like the 40 solar mass star in the heart of the Orion Nebula, has a lifetime of only several million years. How do those stars die? The most massive ones explode as supernovae. So large star, massive, becomes a red supergiant, explodes as a supernova. If the star is really massive, 20, 30, 40 times the mass of the sun, it forms a black hole. If it's only 8 or 10 or 20 times the mass of the sun, it'll form a neutron star, an object about the size of the city of Boulder with the mass of the sun. A cubic centimeter, the size of your thumb, would weigh the same amount as a battleship. That's a neutron star. The low mass stars, sun-like stars, they last long. The sun will last about 10 billion years. We're about halfway through. The core of the sun will collapse in an object we call a white dwarf, size of the Earth, but with the mass almost as that of the sun. So let's look at some of these objects. So one of the massive stars that's close to dying is called Eta Carina. This is the Carina Nebula. There's a star right there. It doesn't look like a star when we look at it carefully. It looks like this. This is an image with the Hubble Space Telescope taken in 1999. Go back in 2018. It's grown. It's expanding. In the 1850s, this star became the second brightest star in the sky, lit up the southern hemisphere, almost as bright as Sirius. It's called a Great Eruption. In that event, we think something similar to what happened in the Orion Nebula 550 years ago occurred here. A triple star system involving 2 massive stars experienced a merger. The orbit of one star started interacting with the surface layers of the most massive member. Tidal forces caused the orbit to decay, and in the 1850s that star merged, setting off an explosion that has released about 1,000 times more energy than the Orion event. That's the Great Eruption. And what we're seeing here is about 20 solar masses worth of ejecta flying out at about 600 kilometers per second. It's called the homunculus. In fact, if you ever have a chance to go to Chile with a small telescope, look at Eta Carina. This is about the size of the planet Jupiter, and it's blazing bright. It's one of the most spectacular nebulosities in the sky. Unfortunately, you have to go to Chile or Australia to see it, or South Africa. It's one of the most amazing objects in the sky. All right. Lower mass stars sometimes form jets just like forming stars. This is a dying star ejecting material that's very similar in appearance to the young star jets we saw earlier. Okay. How many of you have seen the Ring Nebula in Lyra? One of the bright summer objects you can see with the telescopes here. This is a Hubble view. This is a James Webb view. This is an object where a sun-like star ran out of nuclear fuel. The core of that star collapsed. That's the remnant right there, and expelled its outer layers. As the core collapses, it heats up to the temperature of almost 100,000 degrees. The intense ultraviolet radiation essentially ionizes the ejected envelope, causing it to glow. That's what makes the Ring Nebula appear like a ring. It's actually, the geometry is not that of a ring. It's really probably like a sphere. And just seeing the edges being a little bit brighter than the center because you're looking through more material. Okay. Now, supernovae, I mentioned supernovae. The most massive stars die in a cataclysmic gravitational bomb, essentially. The core collapses violently when it runs out of nuclear fuel, forming either a neutron star or a black hole. The energy released is something like 1,000 times the Orion explosion. So it'd be something like the amount of energy that the sun puts out over its entire 10 billion year lifetime. All that energy is released in a matter of seconds. The core collapses, the blast wave eats its way through the outer layers of the star over a few hours, and then the surface of the star is blown off with a speed that can approach 5 or 10% the speed of light. And that fireball gets brighter and brighter for a few weeks, and then starts to fade. That's what we call a supernova. If you look at the supernova a few hundred years later, you will see a debris field expanding away from the explosion site with speeds of thousands of kilometers per second, and eventually that slows down to hundreds of kilometers per second as it interacts with surrounding material. The most recent supernova not in our galaxy, we haven't seen one in 400 years in our Milky Way. But in a nearby galaxy, the Large Magellanic Cloud in the south, there was an event in 1987. That was the most recent supernova. When you look with James Webb at the site of that explosion, a few decades later, this is what you see. A ring surrounded by some other rings, and a debris field which is expanding very rapidly. That's the youngest supernova we've seen in the local universe. Okay? We know historically there's been events that happened hundreds of years ago. In the year 1054, the Chinese recorded a guest star, a supernova that was so bright it was visible in broad daylight. Remarkably, there's no record of this in Europe. So all I can surmise is the Catholic Church said, nothing in the sky changes, and therefore you will not record anything that changes in the sky because it's heretical. Or it was very cloudy. That's another possibility. But at the location of the explosion of 1054, we see the Crab Nebula in Taurus. On the left is the Hubble Space Telescope image. On the right is the James Webb image. There was an even more recent explosion about 1667 in the constellation Cassiopeia. That was not seen visually because it's obscured by interstellar dust. But if you look at it at the site of that explosion, we knew about it because it was detected as a radio source in the 1940s. We wonder, why is there a radio source at a specific location in Cassiopeia? What are its properties? We inferred from the radio emission it was a supernova. And then we looked in the optical, we found these expanding filaments. They trace back to an event about 1667. So we infer that was the supernova, and we see its remnant today in this image taken with James Webb. And the next image is the same object, but we also added the X-ray emission from a facility called Chandra, X-ray telescope in orbit. Okay, I'm going to now go beyond the Milky Way, show you some galaxies. This is a nearby galaxy observed with the Hubble Space Telescope. Probably not too different from our Milky Way, if you could somehow see the Milky Way from outside. There's a bright nuclear region. There's a bar, this region here, surrounded by spiral arms, which trail off the ends of the bar. This is the visual view. You see clusters of stars, young clusters. You see dark clouds, which are the molecular clouds which support star formation. And the yellow light is the ancient population of older stars, sun-like stars and older, that are too dim to see individually. Now, if you look at the same scene with James Webb, the stars all but disappear to be replaced by interstellar clouds. And what you're seeing here are the molecular clouds, the nuclear region, and the spiral arms of the galaxy. By the way, the emission here is very interesting. What glows in the James Webb wavelengths is not the simple dust grains made of graphite and silicates, but rather complex organic molecules. In the James Webb spectral windows, the kind of molecules that radiate are known as polycyclic aromatic hydrocarbons. These are molecules built out of benzene rings with various groups of carbons and hydroxyls and other compounds. They're complex organics. The point is that interstellar chemistry in these star-forming clouds, molecular clouds, drives a very complicated chemistry. And we see that something like 10% of all cosmic carbon is locked into these complex organics called polycyclic aromatic hydrocarbons, which have very well-defined spectral features in the infrared. And we can even tell which ones are ionic, which ones are not. Lots of diagnostics can be obtained by taking spectra. I won't bore you with that. There's another galaxy with James Webb, molecular clouds and circumnuclear rings. This is a really interesting situation. We think 3 galaxies interacted. And one, this one, almost penetrated right through the heart of this galaxy, setting off what looks like a splash. Just like we toss a rock into a pond. You get a ring of waves expanding outwards. In this case, the waves trigger bursts of star formation. And so the expanding ripple is lit up by thousands of massive young stars right here. And what does James Webb see? Well, you see the spokes. You see a central inner ring. You see the outer ring where all the molecular gas is. You see some connecting structures. So just like what you would expect when you toss a rock into a pond, except this is interstellar gas responding to the gravitational forcing of the passing galaxy, which kind of zoomed through like this. This is just a montage. This is a project called FANGS, which don't ask me to tell you what the acronym stands for, but it's a survey using James Webb of all the nearby galaxies. We have about 100 objects now we've imaged with the James Webb Space Telescope. All right, let's go a little bit further. We're almost done here. How far can we look back in time to the earliest galaxies? And here's where James Webb has produced a surprise. Now, one of the interesting tools is that the power of James Webb can be amplified by a natural phenomenon called gravitational lensing. When you have a mass of material, the gravitational field of that mass will bend starlight. And so in this cartoon, you have a distant object here, Earth is here, you have a cluster of galaxies in the foreground. The gravitational force of this cluster actually warps space-time, indicated by this grid underneath here. Light rays coming from the distant object can come this way, be bent toward the cluster, reach Earth. But other light rays can reach it from the other side. So we can get multiple images of the same object behind the cluster. The cluster actually acts like Mother Nature's magnifying lens, effectively allowing us to see objects which are tens to hundreds of times dimmer than what James Webb could see without the gravitational lens. So what does this look like in real life? Here's a cluster of galaxies. The yellow objects are foreground clusters, galaxy clusters. So just like the clusters of stars, galaxies tend to gather into groups called galaxy clusters. And you notice these long linear objects curving in every case toward these yellow objects. These are gravitationally lensed background galaxies. This has allowed us to look way back to an ancient time, no more than a few hundred million years after the Big Bang, when we think the very first galaxies were assembling themselves. In fact, we've now seen redshifts, that is how much the wavelength has been stretched since the light was emitted, up to about 20. So we're looking back to within the first billion years of cosmic history. And what we're seeing is that galaxies were very different from today's. Today sees beautiful spiral arms and elliptical galaxies like in this foreground cluster. In the ancient universe, the galaxies are ratty, irregular, undergoing horrendous rates of star formation. The Milky Way is producing, on average, about 2 solar masses worth of stars per year. Of course, the process takes 1 million years. But on average, in 1 million years, you produce about 1 or 2 million stars in the Milky Way. In the distant universe, these young galaxies are forming stars 1,000 times faster. They're converting their primordial hydrogen and helium into stars at rates hundreds to thousands of times faster than any galaxy today. In fact, there's a transition. The early universe was full of gas with very few stars. Starbursts convert that gas into stars rapidly, and as the galaxies evolve, the gas gets consumed by stars. So galaxies today tend to be star-rich and gas-poor. Very little fuel left in the Milky Way to make more stars. Okay. This is just another example. Zooming into one of these little arcs, you can see a highly magnified gravitationally lensed, distorted image of a background galaxy. You can actually see individual star clusters in these distant objects. Okay. So I'm going to end with a couple of things. I mentioned gravitational waves. So in 2015, the instrument called LIGO the laser, the observatory which measures gravitational waves. There's 2 stations. One is in Hanford, Washington. The other is down in, whoops, hang on, see. That's not what I want to see. Anyway, we have 2 LIGO stations, one in Washington State, one in Louisiana. These are 4-kilometer laser interferometers, which allow us to measure the spacing between 2 mirrors to a level that's about something like a millionth the size of a hydrogen atom. We can watch changes in dimensions, much, much smaller than the size of an atom. When a distant black hole, or a binary, a pair of black holes, interacts, orbits each other, the orbits decay and emit gravitational waves, causing space-time to oscillate with a certain frequency. LIGO detected this for the first time from a black hole merger in 2015. And what this looks like is an actual detection. This is actually a neutron star merger in 2017. The LIGO instrument, here's a picture of it. There's actually 2 arms, one here, one here. These are 4 kilometers long, very carefully constructed so you isolate all vibrations, earthquakes, trucks, any kind of noise. We can measure the spacing between these mirrors to much, much smaller than the size of a hydrogen atom. And that allows us to detect gravitational waves. And here's what the signal looks like. This is actually the frequency in hertz, so it's audio frequency. You see this chirp, it goes, disappears. That's what it sounds like. In this particular case, 1.8 seconds after the signal was detected, we saw a flash of gamma rays with 2 satellites. Now actually, what the history of this is that we found the gamma ray flash first. The scientists went back to the data records on LIGO and found this signal. Holy cow, a neutron star had merged. An alert went out. Something like 3,000 astronomers on this planet pointed their telescopes at the suspected location. We didn't know where it was exactly, but we had a catalog of galaxies at known redshifts. And so rapid scanning of the sky found an optical counterpart, a flash of light that brightened over a few hours and within 2 days was gone. That was the first instance of 2 neutron stars merging. And the spectra told us that this kind of process is what's responsible for what's called the rare earth elements. Gold in particular, we think originates in neutron star mergers like this. And in fact, most of the elements heavier than iron form in these kinds of events. In the process of merging, some of that material is ejected, mixed in with interstellar gases, and eventually formed into new stars. The Earth's gold was inherited from neutron star mergers that happened before the solar system formed. Okay? We've seen now several neutron star mergers, but more interestingly, we've seen hundreds, almost 100 black hole mergers with gravitational waves. And this past year, using pulsars, we've also detected what's called a stochastic background. It's back here. Yep. Nanohertz gravitational wave background. We detected using neutron stars. They're perfect clocks. They spin with a precision of order part in 10 to 10th, 10 to 11th, 10 to 12th, comparable to good atomic clocks. By measuring the pulse arrival time from pulsars on different parts of the sky, we can look for gravitational waves which have periods of order, not days, but years, decades. And last year it was announced that over the last several decades, a network of radio telescopes has detected the stochastic background of gravitational waves. So we have a new emerging spectrum, not just light. We can now study the universe using gravity waves. We can detect stellar mass black holes merging, neutron stars merging, and now stochastically, we can see a background of much longer period gravitational waves with frequencies in the so-called nanohertz regime. Nanohertz corresponds to a billionth of a second. That corresponds to 10 to the 9 seconds, which is 30 years. So we can see what's causing it. These are supermassive black holes, the kind of black holes that we see in the centers of galaxies. And in fact, it's possible that some of these gravitational waves actually come from the earliest seconds of the Big Bang. There's a theory that suggests that the early universe, well before the formation of the cosmic microwave background, produced high-frequency gravitational waves which would have been redshifted by factors of billions by the cosmic expansion. So we may have a tool of how to probe the first seconds of the Big Bang. And I want to end with one little thing, one more little piece of exotica. This thing, ice cube. As you know, Antarctica is essentially a huge glacier. It's covered by, South Pole is covered by 2 kilometers of ice. The ice below the top few hundred meters is perfectly transparent to light. And what the astronomers have done is built an instrument using that ice, drilling hot water, using hot water as a drill. You drill through the ice for 2 kilometers, and while the water is still liquid, you lower strings of detectors into the ice, looking not up, but down through the Earth. We actually use the Earth as a filter to filter out particles that we are not interested in. Neutrinos are so penetrative that it can come right up through the Earth and produce flashes in the ice, which can be detected by our sensors. This is called Ice Cube. It's a cubic kilometer of ice that's instrumented. And also last year in 2023, they first announced the detection of neutrinos from the Milky Way. So we have yet another, a third new window on the cosmos. And so we live in an absolutely remarkable time. We are opening new windows. We're seeing the universe in new ways. We have ways of probing the earliest seconds of the universe in principle with the next generation of gravitational wave sensors and even neutrinos potentially. All right. So what is our picture of the cosmos? It's kind of remarkable. If I had told you this when I was a graduate student, I would have been laughed out of the audience. Because today we think ordinary matter, the stuff you and I are made of, makes up something like 5%, maybe 4 to 5% of the cosmos. Something like 25% is something we don't yet understand, is dark matter. We can see its gravitational influence. We know it does not interact at all with light of any wavelength, does not interact with a strong nuclear force, but it must interact with a weak nuclear force. So we don't know what it is yet. We have had huge amount of efforts looking for it. So far, nothing has turned up. We have many candidates, many ideas, some of which are crazy, but this is, to me, one of the biggest challenges. What is the nature of dark matter? What constitutes it? And then finally, the surprise in 1999, 1998. The universe is not slowing down in its expansion. It's accelerating. Einstein was right in adding the cosmological constant, because the dark energy seemed to act just like Einstein's cosmological constant. It's a property of empty space. Empty space appears to have a pressure in it, a pressure which causes any object which is not gravitationally bound today to be pushed away from other similar objects. Now, the Earth is not expanding because gravity is dominating it. And so, we're isolated from the dark energies. It's around us, but gravity dominates over the dark energy. The equivalent density in units of mass is something like 10 to the minus 29 powers of 10 per cubic centimeter. We can measure it. We don't know what it is. These are two of the biggest mysteries. What's dark matter? What's dark energy? And why should you care? Well, I think history tells us something interesting. Over the last 400 years, ask yourself, what has driven the economy of this country? What has driven our technology? I think it's one simple answer. It's not politics. It's not things of that sort. It's science. It's science. The invention of mechanics by Newton and Galileo led to the Industrial Revolution. Our understanding of electricity and magnetism, 1800s, led to the electrification of the planet, to telecommunications, to radio, to television. The early quantum mechanics, our understanding of the atom and how it works, is what makes your cell phones possible, the computer possible. The question I have is, how will our understanding of dark matter and dark energy change our technology in the future? Even if we can't harness it, the technologies used to investigate it will open up new horizons. LIGO, by enabling us to measure separations over 4 kilometers which are less than the size of a hydrogen atom, is a revolutionary technology. How will the quest for dark matter and dark energy change how we live on this planet? And with that, I'm going to stop. I've gone on too long. So.
The light flashes from neutrinos.
Yeah.
Collisions?
Yes, so even though ordinary nuclei in the water or the ice, so the point is neutrinos do interact with matter, but very, very weakly. I mean, we can produce them in nuclear reactors, so they obviously are produced, and we can detect them just outside nuclear reactors with, just by watching them interact with ordinary atoms. What happens is a relativistic neutrino knocks unstable subatomic particles out of the nucleus, and if those things are moving faster than the speed of light in the ice, they produce a kind of purple flash called a Cherenkov flash. And the sensors can pick up that flash, and from the direction of the light, we can reconstruct the direction of the neutrino. And so we have a way of measuring them. By the way, there's a technical term called cross-section. How many atoms can a neutrino traverse before having a 50-50 chance of experiencing a collision? The answer is about 10 to the 42 power nuclei, okay? So if you think about that, that's about the equivalent of a light year's worth of lead. So, and by the way, neutrinos are produced in the sun, but you may not be aware of it because the interaction rate is very low. But in every second, whether the sun is above the horizon or below the horizon to the Earth, neutrinos from the center of the sun are flooding you about 10 to the 13th power neutrinos per square centimeter per second. You are being flooded by neutrinos right now. Most are coming through the Earth because the sun is below the Earth. But you're not aware of them because the cross-section is so small that the chances are that over your lifetime, only a few dozen have actually interacted with the nuclei in your body. So you need huge volumes of material to detect these things, or you have to have extremely bright sources of neutrinos. The fact that IceCube can now detect the Milky Way, I think, is astonishing. It also tells you that there's quite a bit of neutrino flux out there. It's a whole new spectrum that we are just beginning to explore. It's a difficult way of doing science because the IceCube has been under construction since the early 1990s, and for years, all they were seeing is noise. And only recently have they successfully identified discrete cosmic sources. And so we've opened that spectrum, but it's not going to be easy to harness it. Anyway, remarkable time. And if you're young, there's a bright future for you in this stuff. So.
Is that because IceCube is now more sensitive with new technology in it? Or have they learned how to look at the data?
Yeah, I think the latter. The equipment has been sensitive right from the get-go. I think the use of AI and computer machine learning has been a great aid. How to subtract the noise in an intelligent manner. By the way, IceCube is not the only neutrino observatory. There's actually two in the Mediterranean. There's one off the coast of Sicily, one off the coast of France in the Mediterranean, doing the same thing with just ordinary water rather than ice. But the same principle, use photomultipliers, looking for flashes of Cherenkov light from interactions with nuclei.
You spoke of the Webb telescope detecting carbon molecules and things, complex things. Do we find evidence of those types of molecules elsewhere?
Yeah.
Are they all through space, for example?
Well,
or do they break down?
So most of these molecules are in the so-called molecular clouds. So these are shielded environments, shielded from ultraviolet. Objects like the Orion clouds you saw in these pictures are perfect examples. So the most common molecules are obviously molecular hydrogen. Then there's atoms of helium. Carbon monoxide is the next most abundant molecule. It's about 1 part per 10 to the 4th of hydrogen. And then at the level of 1 part per 100,000 to 1 part per million, there's a whole host of organics. We see things like ethanol, we see methanol. In fact, someone quipped, back in I think 1978, Lou Snyder detected ethanol in the Orion Nebula. And he estimated the amount in fifths. And he found there's something like 10 to the 20, I can't remember the exact number, it's a huge number of fifths. And the end of the paper said if you could only tax it, we could fund all of astronomy for the near future. There's some like 10 to 28th power fifths of ethanol in the Orion Nebula. There's an example of a complex organic, but it's ethyl cyanide, methyl cyanide, and these are the simple ones. When you go to the the polycyclic aromatics, we now think there are literally thousands of individual species, maybe millions. But they have certain characteristics. The benzene ring has certain characteristic oscillation frequencies. So at around 10 microns, 11 microns, the carbon single triple carbon bond oscillates with characteristic frequencies. You stick a hydroxyl on one of those carbons, that changes that frequency slightly. So by looking at the detailed spectral shapes with instruments like Hubble, or James Webb rather, we can actually start to tease out what kind of polycyclic aromatics are we dealing with. How many carbons? We think that we have hundreds of carbons in some of these complex molecules. Most of these molecules are found in the dense star-forming cores where massive stars are forming, because sometimes we think the chemistry requires an activation source. You need a heat source, you need an energy source. The energy released by shock waves, the energy released by ultraviolet light probably allows the rich chemistry to happen in these. But inside regions like Orion, the Orion molecular clouds have been one of the most prolific sources of discovery for interstellar molecules. The most powerful instrument for this, by the way, is not James Webb. It's the Atacama Large Millimeter Array. So what's amazing about that site, we combine 55 antennas, millimeter wave antennas, at high frequency, up to 1 terahertz. This is located at 15,500 feet in the Atacama Desert. Why? Because you want a dry atmosphere. You want to be as high up, so less pressure, and you have very dry conditions. And that's where ALMA is. It's in a high, dry desert site in Atacama. And that instrument has now revolutionized our understanding of organic chemistry in space. So if you want to do chemistry in space, ALMA is your instrument.
But carbon has such a high number of protons. Aren't there
Six.
similar atoms that are more prolific?
Yeah, carbon has a bonding which is very rich. For some reason, I'm not a chemist, but carbon has just a prolific way of binding with itself and with other atoms. And so, I think no other element that I can think of has as rich a chemistry as carbon does. So it may not be an accident that life is carbon-based for that reason. So, silicon, in some ways, is similar, but its activation energy is much, much higher, and to drive a silicon chemistry, it doesn't work in interstellar conditions. It does work for carbon. It's also the fourth most abundant element. So the hydrogen is the most abundant, helium second, then comes oxygen, then carbon.
So
that helps.
Skip over a whole bunch of.
Yeah, the point is that the formation of elements in stars favors oxygen and carbon. Specifically because in a star, the first thing that happens is you fuse hydrogen to helium. And then you fuse 3 heliums to carbon. Then a carbon interacts with helium to form oxygen. That, in a nutshell, is why oxygen is so abundant. And carbon next. And then all the heavier elements are rarer because it just takes further steps in the nuclear reactions to get there, until you get to iron. And iron's kind of the grave of stars. When you get to iron, there's no nuclear energy that gives you more energy. Once you have a core of iron in a star, there's only one thing that happens. The core collapses. Gravity wins. You can't sustain the pressure inside the star. The star collapses. Boom. Either a neutron star or a black hole. And the energy comes out as a supernova.